Hello, hello. At the class with me, my name is Ming. Today we're going to learn how to expand a binomial with a rational power. That is something like this: power to the power -2, or half, or a quarter. And this expansion was first generalized by Newton in 1665 as he was exploring or expanding how to expand two numbers, uh, maybe to a fraction, or and so on. So we're going to start by looking at the binomial theorem. So this is the binomial theorem that you are aware of in your formula booklet, and NCR here is just rewritten as this: n factorial over r factorial n minus r factorial. Having said so, when it's written in this particular form, n here is usually referred to as a natural number in this particular form. Where else in the extension of binomial theorem, that is the generalized form, n here is any rational number, that it can be a positive or negative fractions, for example. So here is the form. In the next slides, we see how we can derive this generalized from the basic binomial theorem. So we start by writing the basic binomial theorem. For example, we can expand this basic binomial theorem into like this. That is, replace the NCR by this n factorial over 1 factorial and n minus 1 factorial. And if I do this, and at the same time, I've also taken out a to the power of n from each of the term, all right, from each of the term. So this is what I get. So you can see now, if I simplify, so a to the power of -1 times b, and a to the power of -2 times b to the power of 2 become b over a squared, where else the coefficient can be simplified into this. Therefore, this is basically the extension form or the generalized form. All right. So we go to the next slide. In the next slide, we look at two examples. These, we can hopefully do this fast. So I'm going to, usually this is how I do 1 cube, plus 2 cube, 1 cube plus 1 square plus 1 to the power of 1 plus 1 to the power of 0. And then at the same time, I'm going to write the second part, 2x cube, right? So 2x to the power of, in this case, 2x to the power of 2, and 2x to the power of 3. And notice the sum of the indices must add up to 3, all right, all of them. And then now I put in the coefficient. The coefficient here is 1, 3, 3, 1. So right now at this stage, I can simplify all of this. So this is 1 plus 3 times 1 times 2. This is going to be 6x plus over here is 4. So it's 12x squared plus 8x cubed, for example. So you can, right? So I have 4 terms. When n equal to 3, I have 4 terms. The number of terms in the general form in the binomial theorem is usually 1 more than the power. But in this particular case, this is 3 over 2. What happened? So so we're just going to use the formula given in the formula booklet. So I will start with 1 to the power of 3 half, and then big bracket, and I put inside here 1 plus 3 half, and then 2x over 1, all right, and plus 3 half, and then 3 half minus 1, and then over 2 factorial, and then 2x over 1, everything square, and I continue this particular process. And if you do 1 to the power of 3 over 2, it's just going to be 1. This is 1 plus 3x plus 3 half. And next is 3 half minus 1 is half. And then over here I have 4x squared. And then divided by 2 plus dot dot dot. And the process actually continues. It does not stop. So I simplify a little bit more. So this is 1 plus 3x. Over here, 2 times 2 is 4. 4 and this 4 cancel out. So I get 3 half x squared plus dot dot dot, and it continues. So this is part of the expansion of this particular square root of 1 plus 2x everything cubed. And you can see that the blue and the red are very similar, but the second one is the cube square root of the first. And I also have this particular instruction here. This is just to ensure that I can do binomial expansion for this. The reason why we have this later on, later we will study this in the Maclaurin series. So in here, you can see that what happened now. Well, if you look at the expansion, what do you notice about this expansion? Very good. What's first is that the number of terms in the A is just 1 more than the power. But for rational fraction, this continues. It does not stop because there is no value n minus 1 here, and this n minus 2, n minus 3. It does n, and that is not a fraction. So this process will never get to a point where n minus 1 is equal to 0 or n minus n, as in this case n minus n is equal to 0. Here we never get to that case. So it will keep continue. All right, thank you very much, and in the next video we will see more work